Welcome. In this video, we will showcase the new GuruCE iMX6 BSP for Windows Embedded Compact 7 and 2013. We start by installing SetWINCERoot, a tool that allows us to hard-link the WinCE tree into any folder so we can keep the original CE tree clean. Now we set the link route for WEC7 and 800. And we unpack the GuruCE iMX6 source BSP package into the WinCE-roots folder. Enter the password and click OK. We're just quickly renaming the long folder name for ease of use. Inside the BSP package, you will find Lauterbach Trace32 JTAG scripts, manufacturing tool profiles for all the off-the-shelf boards supported in the GuruCE iMX6 BSP, full source code of the silent bootloader utility, 4 sample OS designs, and of course the full source BSP itself with the extensive catalog, HAB v4 support files, bootloader source, and drivers for many external peripheral chips and nearly all modules inside the iMX6 SoC. Link the WinCE 700 root into our WinCE X00 folder and open the CE7 OS design. You will notice the sample OS design has 5 build configurations: checked, debug, debug flash, release, and ship build. We'll activate the ship build configuration and have a look at what the differences are by opening the project property pages. The kernel you flash onto your production devices should always be a ship build configuration because it turns off the kernel debugger, disables KITL, enables compiler optimizations, is set to generate an image to be flashed to disk, and, most importantly, sets WinCE ship. This last option turns off serial debug messages that have a big impact on overall performance and real-time behavior of the CE kernel. A debug configuration enables the kernel debugger and the kernel-independent transport layer, disables the WinCE ship setting, and creates a kernel for loading onto RAM and debug using Visual Studio. The only difference with debug flash is the IMG flash setting that creates a kernel that can be flashed to SD, MMC, NAND, or SATA disk. The sample GuruCE iMX6 CE7 OS design is configured to build a kernel and bootloader for the Sabre Lightboard. The Set Config option selects all catalog items for every function on the board. By filtering the catalog for user-selected catalog items and dependencies, you can see which catalog items are selected for this board. Checked boxes indicate the item has been selected by the user, whereas a solid green square means the item has been included because another catalog item depends on it. The Sabre Lite has display capabilities through the HDMI and LVDS ports, supports touch, USB host and OTG, has 2 serial ports of which UART 2 is used for debug output, has a micro SD card slot, a normal SD card slot, a SATA connector, no RTC chip, supports PWM for backlight control, supports PCI Express, Ethernet, I2C, GPT, GPIO, FlexCAN, ECSPI, and contains an SGTL 5000 audio codec. The Sabre Lite has 1 GB of memory and is fitted with an iMX6 quad processor. The board is hardwired to boot from SPI NOR Flash, but especially during development it is much easier to use the GuruCE CEWriter tool to update bootloader and kernel images. To support this scenario, we created a tiny bootloader that can redirect the iMX6 boot source at runtime. Here we redirect the boot from SPI to USDHC4, which is the micro SD card slot on the Sabre Lite. In this BSP release, we've added High Assurance Boot, better known as HAB. HAB secures your device by only allowing bootloader and kernel images with the correct signatures to run on the device. Enabling HAB is extremely easy using our BSP, as we will show a bit later. Simple catalog selections allow you to build a bootloader that runs from NAND, SATA, SD, eMMC, or SPI NOR Flash. You can also build a bootloader for the NXP Manufacturing Tool. When your device does not have a bootloader, or you have somehow bricked your device, the manufacturing tool can be used to bring the device back to life. We've included many handy utilities to our BSP, of course all with full source code. There are tools to automatically start your application at boot, to update the bootloader, kernel and boot splash images from within CE, to view the registry, rotate the screen, and we even added a format utility, to name just a few. In this video, we are going to build a kernel not for the Sabre Lite board, but for the Nitrogen 6X from Boundary devices. Deselect Set Config under Sabre Lite and select Nitrogen 6X. The C++ application we have in mind is simply monitoring a couple of GPIO inputs, and based on those inputs, we'll update a GUI and set some GPIO outputs. To minimize the size of the kernel, we don't want to include all drivers and OS components currently selected, so we don't want to select Set Config. However, it is now a bit difficult to know exactly which driver instances are supported on the board, so a good trick is to check Set Config under the board, then set the catalog filter to user selected catalog items and dependencies, and then select whichever items you want to include in your kernel image. We don't want NetIO, CE Touch View, and the Silverlight OpenGL render plugin. Let's keep the GPU tutorials and select Hardware Accelerated Graphics. We are using the OTG port as a client port only with default function serial, and we don't want to include the FTDI USB to serial driver. We do want the Pocket Command Prompt over UART 2, but have no need for the temperature monitor driver. For storage, we'll be using the top micro SD card slot on USDHC3, and would like to keep the time and date valid over power cycles, so we select the ISL1208 RTC driver. We will need PWM for backlight control of the LVDS display, but we don't know which instance to select. All board-specific information is contained in a single folder, so let's open the board header file to find out which PWM driver instance to select. Open the Solution Explorer tab and browse to the Boards folder in the GuruCE iMX6 BSP tree. Now open the Nitrogen 6X board header file and scroll down to Display Configuration. Here you can find which PWM driver instance is used for backlight control on LVDS0. Go back to the Catalog view and select PWM4. We won't use PCI Express, but we will need Ethernet connectivity, so we select eNet1. Touch, audio, and RTC are connected to I2C ports, so we select all of those. Our application will use the general purpose timer to measure GPIO pins periodically. No use for FlexCAN and ECSPI, but we do want backlight and audio. We keep bus enum2 selected for a quicker boot. Now that we have our driver selection done, we can deselect Set Config and see that only the required functionality will be included in the kernel image. If we set the catalog filter to user selected catalog items only, it makes it easier to make adjustments to the core operating system item selection. To reduce the size of the kernel and thereby reducing the boot time, we will remove components we don't need. Our application does not need to be installed using the cab installer, so that can go. And our application will be written in C++, so we can remove the .NET Compact framework too. We'll keep the Telnet and FTP server, core OS services, USB and file system selections, but we have no requirement to play WMA or MP3 audio. We'll keep the standard shell for now, but we don't need any on-screen keyboard. Before we start the build, let's check we have everything set correctly in the BSP Catalog and we're not missing anything. We'll reset the Catalog filter to show all Catalog items and run through the selections again. We have all the applications we want selected, the correct board is selected, and the bootloader will be built for SDMMC. Also, the Nitrogen 6X is hardwired to boot from SPI NOR Flash, so we will use the tiny bootloader to redirect the boot medium to microSD on USDHC3. We don't need any specific cache settings, the correct CPU type is selected, there's no need to enable any rare errata from the list, we don't want to disable precise I/O mapping, we don't need changes to the kernel settings, but we still need to set the amount of RAM on this board, which is 2 GB. We want the hardware watchdog enabled so that if our application misbehaves, the device will be automatically reset. Let's move on to the driver section below. The analog to digital converter driver is first in the list, but ADC 1 and 2 are only available on the UL and ULL processor. If you select these with the wrong processor active, you'll see a red cross. Everything else looks fine, except that we want to use a hive-based registry stored on the microSD card, and we want that card to be formatted with the TexFAT file system, so let's set those options in the catalog. We have enabled Secure Boot, and we authenticate the image using the CAAM engine in hardware. Before we can build and automatically sign our bootloader and kernel image, we will need to generate the certificates, public and private keys. All of this is automated, and all you need to do is follow some easy steps in the included README file. Use a file explorer to open the HAB-v4 folder in the BSP tree, and open readme.txt. Set your passphrase, then run the HAB4 PKI tree batch file in the HAB-v4 keys folder. Set the options you want and let the batch file do its work. When the certificates and keys are created, run the gen srk table batch file in the crts folder. Type the number of keys you have generated and store the key and certificate files in a safe location. Without these files, you will not be able to create a bootloader or kernel image once you have secured the device. That's it! All you have to do now to create signed bootloader and kernel images is build the OS design. Once the build is completed, you can flash the images to the device. If the board does not boot from a removable storage like SD or SATA, and it does not run the GuruCE bootloader yet, you will need to create a bootloader you can load using the NXP Manufacturing Tool. To do this, simply select Boot using MFG tool in the BSP Catalog and set the redirection to the medium you want to boot from. Now, right-click the bootloader folder in the Solution Explorer and click Rebuild. Copy the new eboot.nb0 from the flat release folder to the correct Manufacturing Tool Profiles folder. And modify cfg.ini to select the correct board. Start the manufacturing tool and connect a serial cable between the device and your PC. If needed, set the device boot switches to USB recovery mode and power the device. When the manufacturing tool shows a HID-compliant vendor-defined device is connected, open a Teraterm window and configure the serial port connection for 115/200 board, 8 bits, no parity, 1 stop bit and no flow control. Click Start in the manufacturing tool to load the bootloader into RAM. The boot menu will show in the Teraterm window, and we now have full control over the device. We can now use Visual Studio to flash the tiny bootloader to SPI NOR Flash. Open the project property pages again, and on the General tab type tinyboot.bin. Press OK and set the download medium to USB serial. The default download device in the boot menu should already be set to USB serial, so press D to download. If the download does not start, it may be because the Windows mobile-based device connectivity services are running. Run the Enable USB Serial KITL batch file in the BSP root folder to stop these services and start the download. Once downloaded, press Y to flash the tiny bootloader to SPI NOR Flash and power off the board. Now we can prepare a micro SD card with CEWriter. First, reset the BSP Catalog to build a bootloader destined for SDMMC and rebuild the bootloader again. Insert an empty SD card in a card reader connected to your PC. Start CEWriter and click the Browse buttons to select the bootloader, kernel and boot splash images from the flat release folder. Make sure the correct drive is selected and click Write to write everything to the SD card. Eject the card from your PC and insert it into the top slot of the Nitrogen 6X and power the device. Press the spacebar to break into the bootloader menu so we can set up the board. As you can see, the board booted from USDHC3, and since this is the first time the bootloader runs, it has written the default boot configuration to disk. We can now set up the display. We have connected a 1024 by 768 LVDS display to the LVDS 0 port and a 1920 by 1080 monitor to the HDMI port. The LVDS display is our main display, and we want to clone whatever is displayed there to the HDMI monitor. You can use the bootloader to configure Ethernet interfaces and whether or not you want CE to use a configuration as set in the bootloader. When you've configured everything, press S to save. Since we have enabled HAB for this build, the HAB menu is available and can be used to check if authentication succeeded without any errors, warnings or events. Enter the HAB menu by pressing H and check if HAB reported success without any further events by pressing C. Everything looks good, so now we can write the key to the SRK fuses by pressing W. The output now shows a list of commands it will execute to burn the SRK fuses. The HAB README file tells us to make sure these commands match the output of the fuse commands application in the HAB v4 CRTS folder. The command values are all equal, so now you can type "Yes, I am sure" to proceed. Note that by default, the bootloader HAB code is built with the hash-defined HAB allow fusing set to false, so the code to burn fuses is completely disabled. You can therefore proceed without any permanent changes to your device, as no fuses will actually be burned. After power cycling the device and making sure HAB still reports success without any other events, you can proceed to secure close the device by pressing S. This command allows you to close all possible attack vectors hackers could use to gain unauthorized access to your device. At this stage, if the bootloader HAB code would have been built with the hash-defined HAB allow fusing set to true, the device would only be able to boot correctly signed bootloader and kernel images. We can reset the board so it will load and launch the kernel stored on the microSD card. HAB will authenticate the kernel image and only launch the kernel if it is signed properly. Windows CE outputs its header, followed by the memory layout, and after CE finishes formatting the file partition with the TexFAT file system, the Pocket command prompt comes up on the terminal window. The Pocket command window is simply a command prompt redirected over serial, so we can list files on the device, view the registry, view hardware info, start applications, etc. Using the target control support shell from the command line, we can list loaded modules, running processes, and even kill processes if needed. Type shell -c ? For a full list of possible commands. Use CPU load to view system load per core, memload to view memory statistics, CE updater to update kernel, bootloader and splash images from CE, format -i to view file system information, safe remove to safely eject removable storage, USB FN to dynamically switch or turn off the USB client function, ipconfig to show IP addresses, and reset to software reset the device. We've also included remote control through SIR-DISP and SIR-Host, both on WEC7 and WEC2013. We just built a Windows-embedded Compact 7 kernel and bootloader, but the GuruCE's iMX6 BSP also supports WEC2013. Switching versions is made easy by a batch file in the BSP root folder. Execute the clean BSP batch file to remove all generated files from the BSP. Without cleaning the BSP, the CE8 build system will complain about version mismatches when building the BSP. Now we use SetWINCEroot to link in the WinCE800 root, and we open the C8 Tiny OS design. This OS design is configured to build a very small headless kernel. This is very handy when developing or module testing a device driver or integrated application. If you need to develop a device driver, the BSP includes a template driver that you can use as a production quality starting point for your development. The template driver contains functionality to read settings from the registry, map hardware I/O blocks, set up an interrupt handler and handling interrupts, includes an SDK library and a sample application that uses that SDK to communicate with the driver. We quickly configure the OS design for the Nitrogen 6X board. Build it, and set up the bootloader to download the kernel image from Visual Studio using USB serial for download and KITL. We activate only a single core to avoid the kernel debugger raising exceptions. Enable KITL and save the bootloader settings. The kernel debugger doesn't work properly on multi-core ARM processors because apparently Microsoft never tested that scenario. Execute the enable USB serial KITL batch file again to make sure the Windows mobile-based device connectivity services are stopped. We can now set a breakpoint in the PWM driver initialization code and start the download. We add the PWM driver, SDK and application binaries to the list of modules that will always be loaded from the flat release folder, so that we can unload the driver at runtime using the reload driver application, then change some code, build it, and load the driver again without the need for building and downloading the entire kernel. Note that we don't have to change the bootloader version. The CE7 bootloader can load CE8 kernels and vice versa. Once the breakpoint hits, we can inspect and change variables, set and clear breakpoints, unload the driver, make some code changes, build the driver, and load it again. This concludes the walkthrough of the Guru's iMX6 BSP. If you have any further questions, please contact us through our website. Thank you for watching.